In 2004, my parents bought me a Game Boy Advance SP. Up until this point, my brother and I hadn't been allowed handheld consoles because my parents feared we would disappear into our rooms and just play video games all day. I'm not really sure what convinced them to give in, perhaps my dad becoming addicted to Animal Crossing played some part in it, but regardless, my days of playing Pokemon Ruby in the living room on the GameCube's Game Boy Player add-on had come to a close. Now I could finally put hours into Pokemon Fire Red in the car, and boy did I ever. Several months in, I'd evolved Charmander to Charizard, become the Pokemon champion, and even managed to catch my then favorite Pokemon, Deoxys. But what would my experience with the game have been if instead it looked like this? This may sound like a silly question, and that's because it is one. If I hadn't been able to read the text in the game, obviously I would have bounced off of it, or more likely, not have been able to purchase it in the first place. But the obvious answer makes an important point. To get enjoyment out of them, most people need most games to be in a language they speak. But as we can see here, Pokemon Fire Red was originally made in Japan and written in Japanese. Nintendo of America had to go through and localize the game into English. And when they did that, they didn't just change the text, they also did work to make stuff in the games feel more familiar to Americans, such as changing this Famicom in the player's room to a NES. The NOA localization team had full access to the game's source code, so any changes they needed to make, everything from sprites to the engine's font mechanics, could be changed relatively easily just by modifying the code and assets. But what if you wanted to play a game that never got an official localization? Say, hypothetically, you were obsessed with an anime from the 2000s that had multiple Japan-exclusive games, and 15 years later you wanted to be the change and localize them yourself. Well, you wouldn't have access to the source code, just the game's final ROM image. So, you'd have to resort to So I'm mostly known for hacking the Haruhi games, but that's not what we're going to start with today. Recently, I decided to start streaming, and I had a guy come into our Discord and ask for help hacking the DS game Dragon Ball Kai Ultimate Butouden, as he was picking up a project to translate it into English. I thought it would make for a fun stream to hack a game from scratch, so I'm going to use the 2 streams I did as the basis for my first video. After all, there's no better place to start than from the beginning, right? This is an intro video, so the very first thing I'm going to do is explain the prerequisites for this kind of work. First and foremost, you have to have some amount of programming experience in order to begin hacking for the purpose of translation. If we were just hacking generally, this isn't always necessary. For example, if you wanted to make new levels in Super Mario World, there's already a tool for that called Lunar Magic. If you want to create your own Haruhi visual novel, we're making a tool to edit chokuretsu called Serial Loops. However, if you're translating a game into English, chances are that the game you're working on isn't going to have existing tooling. If it already had some, it would likely have already been translated. So, you're going to need to create your own tools, and in order to do that, you have to have some programming knowledge. This can be any language. I work in C#, but you can write your tools in C, Python, Java, or anything else. Just pick a language you're comfortable with. Personally, I recommend trying to make your tools cross-platform so that future people who want to translate the game into other languages can use them regardless of what operating system they're on, but ultimately it's up to you. Secondly, you have to obtain and familiarize yourself with the tools of the trade. I'm going to be using a bunch of these today, so let me briefly explain the most platform-agnostic ones, and then we'll dive into how I hacked this game. The first and most basic tool of all is the all-powerful hex editor. There are lots of different hex editors out there. A commonly used one that works on Windows is called Hext, but I use imhex, which also happens to be cross-platform. A hex editor allows you to easily view any file's contents in its rawest form, bytes. The hex in hex editor stands for hexadecimal, which is the base 16 number system that can represent the full range of a byte in 2 digits. Good hex editors will provide you with quick ways to analyze data in a file, helping you find text, look at number representations, and also edit files to have different contents. Very useful for testing to see what certain things in a file might do. The other 2 tools are a disassembler and an emulator with a debugger. An emulator is a program capable of running a game on a system other than the one it was intended to run on. So, in this case, we want a Nintendo DS emulator for PC. At the time of recording, the Nintendo DS emulator with the best debugger is NoCache GBA. However, it turns out that NoCache is not capable of running this game. It boots to the Nintendo logo and then freezes. so we won't be using the debugger or disassembler this time around, so I'll save the explanations for exactly what they are and what they do for another video. Now that we've covered the tools we'll be using, we have to get the game. Thankfully, Dragon Ball is a pretty popular series, and after going to a couple of local game shops, I was able to find a copy of this game. Pop it into my hacked 3DS, launch up God Mode 9, and dump the ROM to the SD card. That complete, it's time to get to work. The DS is a new enough console that its ROMs have an internal file system, so the first step in hacking the game is to unpack the ROM. For that purpose, we're going to use a tool that my team maintains called NitroPacker. We just type in a quick command here, and now we have the entire file system of the ROM unpacked. Nice! Normally, the first thing you're going to look for when you want to translate a game is the script files, or at very least some text to translate. Our friend from Discord, however, had already found the game's text. Turns out it lives in a few dead simple files in the MSG, which stands for Message, folder. So let's move on to helping him with what he asked for help with, figuring out the graphics files. I started by quickly going through the file system looking for things that looked like they might be graphics, but nothing jumped out to me immediately, so I decided to take a look at this file in the root directory called archive.dbk.dsa. From the name, we can tell that it's an archive, which is a type of file that contains other files, usually compressed. A common example of an archive you might have encountered is a zip file, which, as you may know, you have to extract and decompress files from in order to view their contents. However, while we know that this is an archive, we don't know how it is structured, so it's time to try to figure that out so we can write a tool to unpack it. Since we're going to be writing a tool, the first thing we should do is get ourselves ready to write code. For me, that means making a new C# command line application, so I'll open up Visual Studio, give the project a name, and create it. A pattern I follow here that I highly recommend people try to follow in general is that I separate out the models and the program functionality, i.e., I put the code that represents files in the game in a separate library project from the code that contains the commands for the CLI. In the library project, we're going to add a new class for this archive. Since the extension is .dsa, we'll call it a DSA archive. Once that's sorted, we can start by opening the archive in a hex editor. Hex editors are powerful tools, but they can seem very intimidating at first, especially if you try to scroll through the whole file all at once. Instead, we'll start at the top of the file, just like a computer would. Usually. At the top, many files contain what's called a header, which is a section of data that contains information explaining how the file should be read. In this case, we can see that this file starts with the bytes DSA, which indicates that it will get flamed on Twitter for viewing leftist activism through the lens of electoral-politics, that it's a DSA archive. Now, the next sets of bytes here are little endian 32-bit integers. We can tell this because of how they're spaced apart. Each is clearly a group of 4 bytes if we look at the zeros that follow them. While I'm not sure what this first one is, this second integer, hex FD5E, looks interesting. It's large enough that it could be a pointer, which means that it would be a value that points to the location of a different value or section of the file. Programs use pointers in files to create a sort of map that the computer can navigate. So let's check what this might be pointing to by going to offset hex FD5E in the file. Looks like we just found a file named nt10000hits.dsf. And immediately after that, we have this header that starts with DSF, which indicates, perhaps, that this is data that corresponds to this file. In fact, if we scroll up, we'll see that we go past a list of file names and then directly into the end of the section we were looking at up top, as these are still 32-bit integers that look like they might be pointers. Perhaps this pointer points to the first file in the archive, the end of the header. Let's put what we have so far in our DSA archive class. Note that we could be wrong about some of this, so we'll treat this class as a living document and modify it as we go along. Next, we have this hex A integer, which corresponds to the decimal number 10. I don't really know what it is yet, so we'll put it in the class as unknown OC, where hex OC is the position of the number in the file, and we'll move along. Our next 2 integers are also hard to understand. 0 is just 0, and hex 5AA doesn't seem to point to anything in particular. It's in the middle of another pointer later in the header, actually. However, hex EDB8 does point to something. This string, /EFF. Because it begins with a slash and has no extension, I'm gonna guess that this is the name of a directory. And if we look at those next strings, they all look like directories. So perhaps what we're seeing here is a table of those. Going back to the top, if we skip 2 integers to this next hex EDBD, we have another directory. Then we have hex EDD1, hex EDE2, and so on. This more or less confirms our theory that we have a table here. However, these unknown values are starting to get out of hand. Perhaps they will become more clear if we view them in a spreadsheet, so let's get started by producing one. As I mentioned, this class is a living document, so the first thing we're going to need to do is some refactoring. We discovered that there's a table of directories, so we should move some of this logic into a different model. In other words, we're going to make a new class to represent the entries in this table called folder and archive. Here's the problem. Since we have unknown values, we're not actually sure where the table starts. We know that each entry is 3 integers long since the name of folder pointers are spaced 12 bytes apart. I picked this hex 5AA value as the first value in the table and called it unknown00 for now. Then, the second value is name offset, and the third is unknown08. Finally, we're going to go back to the DSA archive class and write some quick code to loop through all the entries in the header. That will give us enough to generate a table. I made this code pretty simple. The boilerplate stuff is just giving us options to pass to the CLI, followed by creating the DSA archive and then writing out its unknowns to a simple comma-separated value, or CSV, file. This will let us open an Excel or any CSV reader to view what's going on. At this point, it was clear that my understanding of the file was still very incomplete, as after the first 10 entries, the file names are only occasionally legible, but most are nonsense. However, notice that number, 10. That's the same number as unknown OC, and what's more, these first 10 entries are all directories. Could unknown OC be the number of directories in the archive? It could be a coincidence, but it's something worth going on, so let's change unknown OC to be num directories. Now we have a starting point to work from, so it's time to start thinking about unpacking this archive. When I say unpacking, what I mean is extracting all the files from the archive. So far, we found a table of directories, so it's natural to assume that the data that follows that table in the header might be a table of files. With that in mind, we can go back and examine some of these unknowns in the spreadsheet. I've switched the hex here to decimal, so we can take a look at the numbers in a more familiar format. And when I do that, a pattern emerges. See here, if we take the first unknown 08 and add it to the second unknown 00, we get the second unknown 08, and that holds true for all the directories. Unknown 08 keeps going up as a result, but unknown 00 changes with each directory. Since we have the context that these are directories, I made a guess here. Unknown 00 might be the number of files in the directory. What's more, after some trial and error, I realized that my assumption as to the order of these values in the directory entries was wrong. In fact, the offset of the directory name was the last item in the entry. The actual order looks like this. If we order it like this, we can see that this item starts at 0 and increments by the number of files in the directory for each entry. That means that it must be the starting index into the file table for that directory. Now that we've probably cracked the code here, let's update our class and then move forward to the file table. The first thing we can recognize about the file table is that its entries are not structured in the same way as the directory table, as if they were, this data would be uniform and pleasant. Looking at the hex though, we can see a pointer to a file name every 5 integers, which suggests that the entries are 5 ints long. To represent the file table, let's make a new class for its entries called FileInArchive. We know that it has 5 integers and that the last one is the file name, so we'll put 4 unknowns and the file name in the class. Now that we've done that, we can modify our spreadsheet construction code and reconstruct it to include the file table correctly. Now this looks much more intelligible. There are still some things I don't understand, especially that second integer, but one pattern I quickly noticed was that the length of the file name corresponded to the first integer. It's always one more because it includes the 0 terminator of the string that we can see here in the hex editor. So let's mark that one here. Scrolling down, there are some files that have name lengths of 0 and clearly have incorrect file name pointers. It took me a bit of trial and error, but eventually I figured out that in this case, the second integer actually points to the file name table we saw below the directory name table, which is where it gets the file name. The pointer we've been calling the file name pointer points directly to the file data for these files. So, let's add some special casing for this in the code. The final thing I figured out here was that this last integer exactly represents the spacing from the beginning of the file to the beginning of the next offset. This means that it represents the file length, so we can put that in the code as well. Once we have all this information, writing code to unpack the archive is actually relatively straightforward. All we have to do is make a new command that creates the directories and then loops through them and writes each file to disk. Easy. After we've unpacked the archive, we can pop in and take a look at the files. This directory looks interesting. Res2D contains 2 folders, one named BG and one named Obj. These could stand for background and object, things that sound like graphics files to me. Now that we've found some potential graphics files, it's time to start decoding them. Luckily, we often don't have to reverse engineer graphics files from scratch. There are programs that exist called tile viewers, which can take binary data and convert it into common image formats used in games. The one we're going to use is called Crystal Tile 2, which is designed specifically to be used for DS games. The DS has a bunch of different ways of displaying graphics, but the common ones boil down to 3 main formats: 4BBP tiles, 8BPP tiles, and 8BPP indexed bitmaps. The BPP there stands for bits per pixel. Since a byte is 8 bits, you get 2 pixels per byte with 4BPP and 1 pixel per byte in the 8BPP mode. All of these graphics formats use palettes. 4BPP uses a 16 color palette and 8BPP uses a 256 color palette. That means that the pixel value is just an index into the graphics palette. So let's start by popping into the BG directory and opening one of these files in Crystal Tile 2. We can then change the format over here to GBA 4BPP or GBA 8BPP to try to get an idea of whether there's images here. And it doesn't really look like it. Huh. Well, I'm still pretty sure that this is an image, so my guess now is that this is compressed. As I mentioned a bit ago, files in an archive are often compressed. This means that an algorithm is applied to them to make the size of the file smaller when stored on disk. However, we need to reverse that algorithm to decompress the file before we start working with it, in this case attempting to view it in the tile viewer. I've been ROM hacking for a few years now, so there are some patterns I've learned to recognize in that time. One of those is recognizing common Nintendo DS compression formats. So I took a look at this background in the hex editor and immediately looked at offset hex 40 and said, oh, this is LZ10 compressed. LZ10 or LZ10 is a very common compression algorithm used on the Nintendo DS and a few other Nintendo consoles. Its name comes from this initial hex 10 value that you can see here that marks the beginning of the compression. The fact that the header is uncompressed makes this file a little tricky. If you just tried feeding it into a decompression program normally, the uncompressed header would make the file break, so you have to be able to recognize the compression later in the file. To test my theory that it's LZ10 though, we first need to confirm that the compressed portion always starts at hex 40, and opening up a few other files, it certainly seems like it does. Now we can just use an off-the-shelf library like this one. This is the .NET library Aurora lib that can handle a bunch of different common video game compression formats. So we'll quickly make a new command using this library that takes one of these BG files in and decompresses the portion starting at hex 40, leaving the header untouched. Now that we've run it, let's try loading the output file back into our tile viewer. 4BPP doesn't look right, but when I plug in 8BPP, some clear patterns begin to emerge. The colors are all randomized at this point because we haven't found the palette data. But notice this block of clearly not pixel data at the top. This is something that you might see in files like this from time to time, and is a hallmark of palette data being included alongside the image. In Crystal Tile 2, we can just right-click this data in the hex editor mode and hit Data to Palette Conversion, and it will convert all of that data into colors for our palette, which definitely looks orderly like a real palette might. And if we pop back into the tile viewer, yep, that looks right. Now we can just remove the header and palette from the preview by jumping forward to where the pixel data must start, and we can see the tiled image. This would now be enough to extract this image, edit it, and begin replacing it. Nice! Now we can take a look at the files in the Obj directory. Some of these files are small, which doesn't give us a lot to work with, so I decided to pick one of the larger files in here that has a clear name to give me something to go on. This one is probably going to be a picture of Goku in the end, after all. Again, in the tile viewer, this file doesn't seem to have any sensible image data at first, so let's take a look and see if we can identify any compression in the hex editor. This one is a lot tougher at first, especially when comparing a couple of these files. However, now that we know that the backgrounds used LZ10 compression, we can start by assuming that there will be LZ10 compression in these files as well, which means we should look for those trademark hex 10s. After a lot of comparison, I ended up figuring out that in these files, the palettes were uncompressed in addition to the headers. I found a hacky way of recognizing where the palette started, but our friend from the Discord took some time afterwards and managed to find these two offsets, which determine the palette location and the start of the compressed pixel data, respectively. So with that in mind, we can write yet another command to decompress these, and voila, it's Goku. He's all tiled up, but he's definitely there. Right now, we have enough to allow our friend to be able to modify these images by simply replacing the uncompressed pixel data and then recompressing it and putting it back into the game, but there's a lot more we could do. For example, if we did more analysis, we could maybe figure out the tiling rules for these images and untile them, exporting them as easily modifiable PNGs. However, that's something we can leave for a future video. Speaking of future videos, I hope this served as a good introduction to what translation-focused ROM hacking actually looks like. This is my first time making a YouTube video of this kind, so I know that there will be things I could have done better, so please leave any feedback you have in the comments. From here on out, I'll be working on videos covering how I hacked the Haruhi Suzumiya games, so please look forward to those. Thanks for watching. Yeah, I guess if you want to know when those come out, you should subscribe.